So what we have here is failure to communicate. Now, I don't like it any more than you students, but that's the way they want it. Well, they get it, right? Anyway, but I've spent time trying to decode my brain to get over here to this particular way that they have done the equation. So no longer is b the y-intercept, it's now the slope m, and a is now the y-intercept. And here's the adjustment right over here. And then also you can also see in here the definitions of the variables that we're going to start building the best we can upon what we know about standard deviation and mean, and we'll build that into this least squares regression line. All right, so this video here, we're going to bank the old school stuff, show how it works, and from now on we're going to use technology. But we have to bank the old school version first, and that's where we're going to start. And you'll see this term line of least squares, and that's really what's the meaning of the line of least squares. That's the big question on these on this, right? So, and then I'm going to do this problem here that I've been talking about a lot. I just wanted to get a good approach on it, and I think I got a pretty good approach to bring all this together. The one thing we want to do, as you can see over here in chapter 4, which this is an old, right, this is the basis old textbook that got our new one. But anyway, it shows what we're looking for in here. And notice this observed y minus the predicted y, and we have this equation right here, which is y minus y hat, right? Remember, y is the observation, y hat is the model, and that's like a prediction, right? That's a prediction. So it's no man's land. It's just, hey, we're guessing, but that's very important. Very important, especially, I would say, in anything. I would say anything in your life, you're looking ahead, right? And remember the concept on a motorcycle, when you approach a curve, you don't look straight down at your front tire, you look through the curve. When you're turning, you look through the curve. You look ahead. Same concept. Just, hey, we're guessing, but that's very important. Very important, especially, I would say, in anything. I would say anything in your life, you're looking ahead, right? And remember the concept on a motorcycle, when you approach a curve, you don't look straight down at your front tire, you look through the curve. When you're turning, you look through the curve. You look ahead. Same concept I had once in an engineering class. We were talking about making drawings, and the idea, if you want to draw a straight line from here to here, you just don't go here. You focus on the dot. Let me see if I can get it together here. And there we go. See, pretty good straight line. I looked to the future. I wasn't caught in the present. So that's what these things are. And I put in a video that was pretty good. It's a channel on YouTube. It's called, it's all about optimization. And one of those examples was the line of least squares. I put that into the announcement on those JRO 8+ series that are dealing with linear regression. Oh, I don't know how that popped. Oh, I got rid of those. Oh. Key thing coming up for week 4. Mutually exclusive, not mutually exclusive. We will be getting into what we would call conditional probability. And from there will be models, the normal curve, and the binomial. We'll do binomial models. But sorry to get off on a little tangent. But anyway, that just so you can see, that's what we got coming up here. So here we are. Once again, we're going to define the curve. And then what I will do, this is one I've been bragging about, talking about, the club head speed. I will do the club head speed in Desmos as just a reminder again of what this least squares regression line is. But we're going to bank the old school, and now we're going to use technology, assuming they are following this method, right? Anyway, we have to trust them because we have it banked. So let's just look. Let's look at a few of these concepts. So, you know, we are basing this on the slope-intercept form, what I often refer to as the most famous linear equation of all times, an analogous situation to Rudolph being the most famous reindeer of all. It's getting that time, right? It's July. Are the Christmas trees coming out yet? I wouldn't be surprised if they are. Once again, we're talking about an independent variable, x. That means x can be whatever it wants. But one thing is interesting is a lot of these, it's just a relationship. It's not necessarily a prediction. It could be a good relationship. And that's where we get into correlation does not imply causation. There's a, I'll talk about that some other time. Anyway, then we got y, the dependent variable, the outcome, or the response. So you'll see this. You might see this switcheroo of these terms. We'll start calling y the response variable and x the predictor or the explanatory variable. I think we transition over that. We did in the other textbook, but we might just hold on to what we have here, but be aware we might transition over there. Once again, M is the slope. V, sometimes called C, is the y-intercept. Here's the basis of the least squares because it's the sum of the least squares residuals. A residual is a difference between the observed y values and the predicted by the line. Y hat, right? Y hat is the model, the predictor. Y sub I is like an observation at I, which is really x. But anyway, and n, again, remember that's the total in your sample. And that's one thing we're going to start breaking apart. Let's see if it's in here. So yeah, there it is. There it is right there. See if this concept is in here. And it's right here. Starting to see that we're making calculations here, or the technology is going to be doing this, where we have the standard deviation of the y variables. See that SY? That's what that is. And then notice in the lower part, we have the standard deviation of the x variables. I thought it was x over y, but this stuff, this is interesting stuff when we start getting down into the nitty-gritty details. I have done it with some very simple problems by hand, but nothing complicated that would... I'm going to use Excel. I might show you an example of that. But anyway, notice that that's the standard deviation of the x variables. So we would have to have a sum of the x variables, do the typical subtracting away from the mean for both the x and the y. And one thing we want to be sure to focus on here is notice that this old school one calls it defines the label here as B of 1 and B of 0. The textbook uses something else, but remember that's just a name. A rose by any other name is going to smell just as sweet, right? So you can plug in whatever you want. You can assign these variables however you want. That's one thing about in computer programming. You always want to have variables that clearly identify and are separate from other ones. When I taught discrete math, and that's one thing I do in my head is I just switch the variables. But the students, they were computer science students, so they were like, hey, we got to have the variables. We can't switch them around. So I'm like, okay, I will follow that, because yes, a computer would crash if you had variables meaning the same thing, right? Or it might not crash. It would just tell you error, ding, ding, right? You might get something like that. Anyway, there's that. And notice what the intercept is. So this is the slope. We'll see what the variables are going to show. Oh, we can look right here. Let's look at what they're using. So here is the y-intercept, or what they're calling over here in our formula sheet as b naught. Okay. And notice it's right here. It's given in this problem. And B is what they're calling, which is weird. Notice what they have over here. They have the slope as B1. Let's just roll it up into the universe and redefine it as what we have right here. Then they got the slope, so I guess that's based upon traditional, that's how it used to be done. A lot of these times these variables get assigned by somebody, and then they attach themselves to assigning these variables, and of course the human factor and ego and all that stuff, it ends up, and then, like I said, statistics is one of the most variable term switching, different terms for everything I've experienced in mathematics at this level, anyway, at this level. So you can see, then we over here, we get the mean, and then we get the standard deviation. And notice that we're talking about the mean for y. This is the mean, standard deviation for y. This one right here is the mean and the standard deviation for x, right? That's for x. Okay? So you can see how this is breaking down. So now we've got to upload what we know about standard deviation and the mean. We did that chapter 1, chapter 2. We banked that the old school way, and now we're using technology. Because we got to speed it up, economies of scale, more resources, less time on each problem in the homework, and vice versa. So report the regression equation using arm. So it's like this then. The x value would be height, and the arm span would be the y. So notice that's what they did. We have an equation over here, and then they translated that over into one of these equations. So once again, that's the slope. Let's go ahead and say that that's m. B is m. So we need a 177 as the slope. Notice that has it as the y-intercept. There we have it correct, and there we have it correct. This is incorrect. So we only got 2 we got to choose from. Okay. Oh, height. Height is the variable. That's the y variable, so that one's gone. And so our answer here would be that one right there. So it's just an exercise in knowing the little pieces of this linear regression. Guys, this is actually not that hard. It's just weird the way it's been presented over the years, I would say. Just my humble opinion on that one. And then now we're going to determine these values. Let's go back over here. And what is B again? B is the slope. B is the slope. You got to recode it. If you need to recode it, recode it. This is the mess we have. That is statistics. That makes it more complicated than it should be. Anyway, I lost track. Here's what the slope formula is. That's what the slope formula is. So let's record what we have for R. For R we have up here 0, 9 or 0, 5, 8, 9, 0, 5, 8. Round to 3 decimal places. So I got a 906. We got a 906. Alright, I don't even know if I'm doing this. I don't even have my notes up. So we're going to do this real live. Let me know in the comments or wherever an embarrassing post or email about any mistakes I make here. That looks good though. Rounding to 3 decimal places. And then one thing I want to notice, like, then it does this. So we're going to do all this old school stuff, and then down here, notice that this one says you're going to use the regression equation from part A, which is going back to this right here. So keep the float levels when you make the calculation. Okay? Because this rounding is going to change it, and you're not going to be in the right margin of error for the answers. And you get it wrong. Hey, I was off by a half. Why are you being so freaking crazy like that? Right? Anyway, that's just a note to take. So for the standard deviation of Y, we got it right here. It's arm span, so 7.74 would go right there. And that's how we would calculate it, right? And then standard deviation of X from up here, standard deviation of X right here, 3.907. All right, and then this is the slope. Let's calculate the slope. B equals, and then we need the R, right? We need the R, and then we need the standard deviation of Y over the standard deviation of X. We have 7.74 over 3.97, and the R was 0.096. So I think you use the rounded value. I think that's what you want to use to get the accurate answer on there. Okay, let's try it on the Desmos. Let's try our calculation. 0.906 times 7.74 over 3.97. And that's what I got there for the slope. Notice that it told us in our model that it was 1.76. So I just want to take a moment to bring up the answer sheet. What did I get? I'm just going to say 1.872 for now. Pause a moment while I find the answer sheet to make sure I'm heading in the right direction. Okay, so I found the answers for this one. I'm using the same numbers they have. 9, oh, there we go. That's it. We got it. We got it. So, there we go. Type a typo right there, 0906, and that's a correction on that number right there. I thought there was something. I was suspicious of something there. What did I get? 1.76. 7.66, which would round up to 1.77. So there we go. Now we got it matching. Now we got it matching. All right. Now we need the mean of y. That's the mean of y, right? Y bar, right? Mean of y, of all the y's. And this one right here is the mean of all the x's. And then A is the y-intercept. So B, in some groups, is the y-intercept. Remember, most famous reindeer of all, right? They're just confusing us all by using different, but they have a reason because these variables are different and unique. But you're going to see this overlap of variables, which will drive you up the wall. But anyway, so we have this. The mean of x is right here, 63.77. 63.77. And the mean of y is 7.74. No. There. 159.7. So that's another brain stretcher, is making sure you got these separated, because that's what I automatically went over here. My eyes went over there. That's where these errors happen. And that's a good point. When you see an outlier, that might be an indication that there was some sort of input error. So, I mean, it could be that the textbook is giving you an outlier. But the first thing when you see an outlier is to investigate further, right? Remember that rule. We learned that way back when. And then we got the A, which was the B, and then there should be a formula right here. There's the formula. There is the formula right there. So if we're going to calculate B, or what are they calling it? A. They're going to call it A, and it should be the mean All right, was looking at too many things, couldn't figure out which was a paper and which was a window, and now I'm back. This is what we're focusing on here. I was thinking of a residual, but A, which is what? A is, what is A again? A is the y-intercept. Okay, you got to reprogram. A is the y-intercept. Now let's go back to this formula. The y-intercept should be the mean of y times, we've substituted that for A. They're calling the slope B, right? They're calling the slope B. This is, all right. So we're back over here. We're back over here. This is why I had to pause a moment to try to do this, because it's a freaking, I don't know. So we're calling the slope B. That's what's getting me. That is totally crisscrossing my brain. And the formula then should be that times the mean. There we go. So now let's calculate A here. The mean of y. A. That's not his pencil. Alright, I guess dog stealing pencils. I guess that's an indicator that there's not enough playtime being executed by the master of the dog. And he's letting me know. Let's go back to where we're at here. So let's put in the mean of y. the mean of y was 15977. 15977 minus, I gotta recode. They're calling B the slope, remember? So it would be 1.77 times, and then the mean of x is right here, 63.77. All right. Let's calculate this one out here. 159.77 minus 1.77 times 63.77. So that should be our y-intercept. So 4690, and then what was the other one in here? There must have been another problem or another question. So anyway, we got that one, 46. We got that one, 46.897. So rounding to 2 decimal places, 46.90. There we go. Is that what they, let's look at the answer sheet. Yes, so, and then the predicted arm span. So that's the only thing we got left. Okay, but this will be interesting. Let me go ahead and test this out. I'm going to get rid of these. I'm going to create an equation. Create an equation, which we should have right now that we just derived. All right, so this is the one we just derived. Y hat equals 15977 minus 1.77, and then this is where we are going to put the x, right? Which is the same thing as saying we're predicting arm span, right? Arm span. And here's our y-intercept. And then we're putting in height. Okay, that's our variable, right? And this is what we were going for. This was the assignment. Okay. Arm span. Independent variable predicting. It's predictor variable, response variable. Independent, dependent. Predictor variable, response variable. So there we have what we have for our equation. So let's try this and see how accurate it gets. Yeah, let's just go ahead and put it to the test and see if it does say to go back. So I do suggest you go back and then what are we predicting? We're predicting at x equals x equals 62. That's a 62 equals height. That's an assignment right there. So we would put that in old school fashion here. It would be 1.5. Oh, it's not 1.5. It's 159. 159.77 minus 1.77 at, as it says, a height of 62. We would plug in the 62. Let's test it and see what's going to happen with it. See what we get. Get 50.3 Y. Hold on a second. So again, I suffer so you don't have to. What I ended up doing. 146.9. So something's still not right here. Something's still not right, and let's see. Hold on a second. Okay, error spotted. I don't know why, but that was a positive slope. That was a positive slope. So these should be additions. I don't know where I got off on that. I think it was looking at too many, no excuse. Anyway, there we go. We got it. And I don't know where the answer sheet, but anyway, that is what the answer sheet says, is 156.64. But let me pause here and try to find that answer sheet. Yes, this is the possibility here. Notice they have the answer of 156.9. We got 156.9. So let's look at how it wants to round it. So now to see how it wants to round it 1 decimal place. So we got a significant figures, a float level thing going on here with the rounding. This is an interesting situation because you'll see this often. Remember what it said? It said to use this equation. It said to use this equation. So this y-intercept would change to 47.16. And I'm going to go as far as it gives me, which is usually the procedure. You don't round until you've made all of your calculations. So now we would do 176 tree niner 522 tree, and then there we go. Okay, 156.5. Still evaluating at the 63, 62. There, I got 150 still. So I'm hoping they're going to give you some leeway there, but I think that did go up just a little bit. Just a little bit, but not much. So be careful on that one. Let me know if you run across anything like this where it's a, I just did it in front of everyone and I got a different number than what they have. It should give you a level of error, but sometimes that level of error seems a little strict, more strict than it should be. Anyway, key there, I would say make sure when you do this last part, use the regression from part A. And that's it. That's the problem. I apologize. I was suffering again, so y'all don't have to. So next, we'll do the club head speed. I'm going to pause, take a quick break. I'll be right back.